In the next few videos here, we're going to be working our way towards developing Gauss's law, which is the first of the four Maxwell equations, which are the key equations of electricity and magnetism. So as our first stepping stone to that, we want to think a bit about the use of symmetry in physics. And a lot of times, some symmetry considerations can reduce greatly the amount of computation you have to do. So let's start with defining symmetry. A physicist would say that an object possesses symmetry if, after doing something to the object, it looks exactly the same. So let's just start by thinking about a cylinder. And let's say that this cylinder is infinitely long. Okay. Now, first off, we could imagine that we just plain slide the whole cylinder to the right. If it's infinitely long and there's no surface defects on it or anything like that, wouldn't it look exactly like it did before? Yeah, it would. And we would call this an example of translational symmetry. So this is where the object looks exactly the same after you move it in some direction. But that's not the only symmetry that our object could possess. For instance, here we could imagine, let's slide that down there. Instead of translating it, we could just as easily imagine rotating it about its long axis. And we could rotate it through any angle about this axis, and it would look exactly the same. So we would call that an example of rotational symmetry. We can also talk about, say, if we take our cylinder here, so let's make another copy of it. There we go. What we could imagine doing is reflecting it about some plane. For instance, I could imagine this plane here. And what I could do is I could swap end for end across this plane. So I could take some point here and I would swap with it its equidistant point on the other side of the plane. This is known as a reflection symmetry, or a lot of times physicists get fancy and call it a parity symmetry. We could do it about that axis. Another example here is we could imagine doing reflections about the axis that contains the center line. So we could pick a point here, say, and a point there, and swap them like that above and below the plane. And again, the whole thing would look exactly like itself. So what this allows us to do is, if after we do some sort of symmetry operation on an object, and it looks like itself, it better be the case, say if we're thinking about an electric field, if this is a charge distribution, the electric field would have to look the same too, or else we know we would have done the thing. So as an example of that, let's imagine let's imagine our infinite rod of charge one more time. Paste another one there. So now here we want to think about what could the electric, if we say that this has a charge, let's go with plus Q here. And it's uniformly distributed. What could the electric field possibly look like? Well, the thing is it couldn't, say, look something like this, because since the whole thing has a reflection symmetry, if I were to go and do the reflection, after I reflect it, the electric field lines would be pointing the other way. And then I could tell that I had reflected it. But since the object looks exactly the same, that doesn't make any sense. I should get the exact same electric field after I reflect it. So that puts an awful lot of constraint on what our electric field could possibly look like, and it's not going to look tilted off. So after a bit of thinking, we realized that the only way this could possibly work is if the field lines are coming straight off the object. Like, oops. Here we go. Like so. That way, if we reflect it end to end, the electric field lines are still coming straight off perpendicular. And that turns out to be the only choice that can possibly reflect the symmetry of the situation. We do have to be a little careful yet. We haven't thought about what happens if we look end on. So if we look at some cross-section of our rod, the cross-section of the rod would look like this. And we realize that we could not have, say, the electric field lines heading off like this, for instance, for exactly the same kind of reason. It would be okay for rotation. It would still look like itself on rotation, but again, on reflection, the electric field lines would end up pointing the, it would end up pointing the opposite way, like that, and then once again, we would know that we had rotated it. We would know that we had reflected it. So it can't possibly be, say, set off to look like a pinwheel. The only possibility then that we are left with as we look at end on is that the lines also come off perpendicular to our cylinder everywhere. And then, no matter what plane we choose, vertical, horizontal, any tilted plane, no matter what we do, it will respect reflection symmetry. And so, believe it or not, in this particular case, we have actually pretty much solved the electric field. We are only down to just figuring out the overall numerical value, but we have completely figured out the functional form from symmetry alone. So these sorts of symmetry considerations make things very straightforward to look at when symmetry is there. It can really make the problem easier. So officially there are 13 possible symmetries that are nice in physics, but really only 3 of them count. So we'll go ahead and hit the big 3 symmetries. So we can say that an object possesses planar symmetry. So here's like a basic example here. We could imagine, say, a sheet of charge. And it has to, in planar symmetry, it has to respect translation in x and y. Should probably use a different color to indicate the symmetry operations here. It has to respect translation in both x and y. And it has to respect reflection about any plane that cuts through perpendicular. And in a case like this, say if we look at our electric field, the only electric field you can possibly have that will do the job is one that comes off perpendicular everywhere. Now, this would be sort of like a basic example of the symmetry. A more complicated example would be, say, if you had a parallel plate capacitor. We would have two objects that respect planar symmetry. And then we could apply superposition to get that overall. We have to have an electric field that runs like this. And again, if these planes are basically infinite, we're done. Okay, the example I had been doing is an example of cylindrical symmetry. So the prototype example is, say, an infinitely long cylinder. And so here we have to have translational symmetry along the long axis, and we have to have rotational symmetry about the long axis, and we have to have reflection symmetry about every possible plane that cuts through the long axis. And all those considerations combined give us the, say if it was a charge distribution, the electric field that we already thought about earlier, where it's just coming off uniformly perpendicular off the cylinder in all directions. And maybe a bit more complicated one would be, say, the coaxial cable that you have from the cable company. You have an inner conductor and an outer I need these to be a little more concentric. There we go. You have an inner conductor and an outer conductor with some insulating material between them so you don't short. And when you're and again, this turns out to be another kind of a capacitor. And it turns out that the capacitance that we have in this wire limits the bandwidth of how much data you can send down the cable. But this is a more complicated example. And again, you can apply superposition, look at this, think about the symmetry arguments, look at this piece here, think about the symmetry, apply superposition, and go from there. Finally, the last of the big symmetries that we tend to stress is spherical. So, say we could imagine having a ball of charge. There's no translational symmetry whatsoever. However, what you do have is rotational symmetry about any direction you like, as long as you're going around the center, and reflection symmetry about any plane you like going through the center. And so the electric field, if this is again a ball of charge, the electric field that you get is just basically heading off radially in all directions, sort of like the quills on a porcupine or something like that. And again, more complicated example, admittedly this one a bit contrived, would be, say, if you had an inner spherical conductor and an outer spherical conductor. Again, you could apply spherical symmetry arguments on both of them to and then apply superposition to get the more complicated answer. Now, there is a bit of a caveat. So far, I've made it look like if we can apply symmetry to something, that we always definitely get the answer. But that isn't always the case. Sometimes all you can do is exclude bad answers or have some rough idea of the right answer. So here, let's look at a finite rod. So let's imagine a finite rod, again, carrying charge plus Q. And we're thinking about how could the electric field near the surface of the rod look. Well, one way it could look, and this turns out to be the correct way, would be like this in the immediate vicinity. Something like that. That would be roughly, this is roughly right. However, by symmetry, we could not exclude the possibility that it looks, say, something like, there we go. Say something like that. Now, here, so this is allowed by symmetry. But it is wrong. Because the big symmetry we have with our finite rod is it has to respect a parity symmetry or a reflection symmetry about its midpoint. And both of these do that. There is no translation symmetry, so we can't apply that here in this case. If you move the rod, you definitely know you moved the rod. So, but here you can use your common sense. You know from the rules of drawing electric field lines, as you get far enough away, this is going to look like a point charge. And so far enough away, the lines should be heading out radially. Whereas here, what's going to happen? They're going to like collide together and then back out. That makes no sense. So although it's allowed by symmetry, this doesn't actually happen. So you do have to combine symmetry with other arguments sometimes. Alrighty, so in the next video we will go ahead on our journey to Gauss's law by defining and looking at electric flux. Catch you over there.